Hello, welcome back to Quantum Computation Simplified. I'm Kadresan. In this video, we'll try to learn something on quantum cryptography. You know that cryptography is a very vast subject. We can't cover the entire scope in one particular video. We'll be focusing more on how to apply Grover algorithm for symmetric cryptography. Okay? we let's try to answer this question: why quantum cryptography? Quantum computers can prime factor faster than any classical computer. That's the key aspect of source algorithm. We know that, right? Qubits exhibit many quantum state, leading to identify passwords keys faster compared to classical algorithms. So that is what is given in Grover's and Simon's algorithm. Quantum parallelism can hasten the process of decryption. We have not talked much about this. Maybe we'll cover it in some other video. So with this knowledge, we can say that there is a threat for the existing cryptography approaches. So that's why actually government agencies like NIST and others, they're spending a lot of money. Okay, so research is already on for post-quantum cryptography, so that things will be secured against cryptanalytic attack by a quantum computer. So everything will become quantum proof or quantum safe or quantum resistant. But people also will argue this way. So possibly, though we accept that there is a possibility of breaking RSA algorithm, particularly for asymmetric encipherment, but quantum hardware, the currently whatever is available, will not support, and we know why. Correct, but there are a lot of main issues, particularly the availability of number of qubits, which is very less, and issues like decoherence and noise. So all these things make the current quantum hardware not capable of breaking RSA algorithm. But we are very much sure that once a good hardware is available, this is going to happen. Similarly, researchers are working on different types of breaking symmetric encryption, and they have come out with nice solutions, and also they are working on how to improve their design for lower depth and width of circuits, meaning less number of qubits and less number of gates and number of stages. Our aim is not to break officially, but once we know that if it can be broken, we will be building a more rugged methodology. So that is the intention of making this video. Okay, I'm sure most of you may be aware, well aware of cryptography and cryptanalysis. But for those who do not have some knowledge on this, we will go through some of the major headings on this subject. There are different mechanisms available. Yeah, before that, let me say what is cryptography. So, cryptography is the art of hiding messages, and cryptanalysis is the art of decrypting. So when a sender wants to send information to the receiver, he doesn't want others to see. At that time, he will be hiding the message. But the adversaries will try to catch that hidden message and try to decrypt. So we are going to see how to do the decrypting for a particular type in this video. So as I told you, there are three mechanisms: asymmetric key encipherment, where we have public key, private key setup; symmetric key encipherment. So maybe we can see this block diagram to understand what is symmetric key encipherment. So the sender wants to send some plain text, some message to the receiver. So what he does, so he takes the key, a secret key, and then encrypt. He may use different encryption processes, and then sends only the encrypted message. We call them as cipher text and the receiver, he uses the same key and then he decrypts and gets the original message. So this is how it operates. So if somebody, an adversary takes this information, he will not be able to decrypt because he needs a secret key. Okay, and there's another method called hashing. Okay, I will not go very detailed into the cryptography aspect of the need, but we'll be focusing more on how to use Grover algorithm for a particular type of cryptographic method. So we will be seeing only symmetric key encipherment. And as far as crypt analysis is concerned, again there are many methods. Ciphertext only. So in this approach, you have a set of keys, and the sender will pick any one, encrypt, and send it to the receiver. The adversary can do some brute forcing with all the keys and try to get the plain text information. Non plain text is another approach. That's what we are going to see today. So in this approach, the adversary is expected to have at least one pair of plain text and the corresponding ciphertext. Okay, so from these two information, he will try to extract the secret key. When such scenario will happen, yeah, we can imagine the sender initially sends encrypted information to many people, and after some time the secrecy portion of that, it loses its secrecy, and the original information is available in public domain. So at that time the adversary will have a pair of ciphertext and plain text, and later, and from that he will extract the key and keep it with him. After some time, if the sender wants to send another information, this guy can make use of the key available with him, the key which he extracted from a pair of plain text and ciphertext, and tries to get the information. So that is what we are going to see today. And there are some more methods called chosen plain text, chosen ciphertext. It's something similar to this. Again, if you want to know more about that, you can get it in any textbook on the subject. Under symmetric key encipherment also, there are many categories, starting from Caesar cipher to the latest AES, Advanced Encryption System. And there are many more which I have not listed here. But in order to understand the process, I'm going to use only a very simple XR cipher. But whatever method we are following in this video, that can be applied to any of these symmetric ciphers. So that's the important thing to be noted. I'll also try to touch upon a type of AES so that you have a better understanding of the various processes involved in AES or any other symmetric cipher. Okay. Yeah, I'm sure that again most of you will be aware of Grover's algorithm. For those who do not have much knowledge, we'll try to have a quick recap of what we have learned. And if somebody wants to know more about Grover's algorithm, I request them to go through my previous video on Grover's algorithm. Okay. So what is it? It's a quantum algorithm for finding the input value of x star of a function f of x, with f of x star equal to 1 and f of x equal to 0 for all other values of x. Yeah, little long sentence. Maybe I'll put the the statement in a different way. Assuming that we have set of x values, maybe 100, 1000, 1000, 1 lakh, right? So we have a number of x values and we have a function. The speciality of that function is it returns 1 when the x what is passed on to this is a special x, what we call it here as x star. At that time it will give 1, and for all other x it will return only 0. Okay. In order, our aim is to, the Grover algorithm helps us to find out what is that x which we are interested in with minimum number of queries. So that's the advantage of Grover's algorithm. So for that we need to build a Grover oracle first. So what does it do? So it will take all the x values and keep them by generating superpositions. Okay. And then when it also will have another qubit in minus state. When all the possible combinations of x are passed on to this Grover oracle, as we know that for that particular x state or x value, the f of x will return 1, and because of that the output is given here as -1 to the power of f of x. So at that time, for a given that particular x, you will have -1 to the power of 1 x state, or get x. So -1 to the power of 1 is minus. So that is what happens. That is, out of all x states, the one what we are interested, it will have a phase getting added. For all other states, f of x will be 0 and nothing happens to the phase, and these states will come as it is. And that is done by the trick called phase kickback. Again, you can see more on the video on Grover's algorithm. But we should know that it just marked what we are interested in. But when you make a measurement, we cannot see the difference, because still the probability is same like any other x values or x states. So in order to increase or amplify the probability, Grover's diffusion operator is given. So this is very interesting one. It amplifies. Okay, here we mark what is to be amplified, and here we are amplifying it. And the interesting part you can see here, this doesn't depend on the problem what we are working. It's all standard stuff with the Hadamard gate, ket 0, bras 0, identity matrix, and another Hadamard gate. Correct? And when we do this operation, depending on the size of the problem, we may get the required state in high probability. But if we are not getting it, we have to repeat this process, particularly when the size of the problem is very high. The input is having a very large number, we have to repeat. So how many times you have to repeat? Square root of n times, n being the size of the problem. Okay, that is theoretically. Practically you don't have to go to that level. Even much before that, you will see a difference, a distinct difference between the interested state and the remaining state. Right? So now we know what is Grover's algorithm. We know a little bit of cryptography. Let's try to implement Grover's algorithm for quantum cryptography. So first we need to decide which cipher we are going to work on, because for that cipher we need to create quantum gates. So in this case, in order to make things simple, I'm using a simple XOR cipher, meaning we are having a plain text, we are having a key, we need to generate ciphertext. So that is the typical process of encipherment, right? So what we are doing here is simple XORing to get the ciphertext. This is, after that we need to do some more things here. We need to load plain text. We are loading plain text. Create superposition of keys. We are creating superposition of keys. So I'm going to I'm just explaining with just 2 qubits instead of 8 here, but the real life problem will have hundreds of bits. Okay, and these Hadamard gates make the superposition, meaning it generates all possible combinations of 2 bits. So in this case it is 00101101. So everything is possible from at the output of these 2 gates. Load known ciphertext. So this is known ciphertext. Then I have some ancilla bits to compare the known ciphertext with generated ciphertext. Okay, we will be applying Grover oracle, Grover diffuser operator, and then we'll repeat the process after doing some uncomputing. We will see later, depending on the size of the problem. I mean, the repetition is purely dependent on the size of the problem. So we need to build the oracle. So this is the oracle, whatever you see here. So at this point we will have all combinations of keys that will be combined with the plain text, so that we will get all combinations of ciphertext at this point. So that will be compared with the given ciphertext here. Okay, if they are equal, then it will flip the value here. So that exactly which we are interested in. So out of so many possibilities, it will mark what we are interested in. Okay, because we have earlier seen that we know one plain text and ciphertext combination to extract the key. So once it is marked, afterwards we need to apply Grover diffuser operator to amplify the probability, and we have to repeat this process and the next one. I have not shown the Grover diffuser operator, but later you will see it when you go through the code. Sometimes we may need more than one pair of plain text ciphertext combination. When such scenario occurs is when more than one key is detected to give the ciphertext, okay, to match the given ciphertext. So it's not a big problem. We may have to repeat this step parallelly here with the second PTCT combination. Will be doing same thing, but to set this qubit, we will be taking information from there also. Okay, so that is how it is going to be done. But in this case, we are not going to have such a problem, so we need not to worry about that now. Okay, now let's see the code. You will have a better understanding. So this is code. As usual, we need to import some of the required library functions. Actually, I have done more than what is required, so it shouldn't matter. Now, this function loads the input like plain text, ciphertext, and the operation is very simple. So whenever there is bit 1, you add a X gate. If it is bit 0, leave it as it is, so that the qubit will be in 0 state. Then load key. So it's not only loading the key, but also generates the superpositions. That is done by the Hadamard gate here. Then this is the cipher. So as we have seen, our cipher is very simple, XORing. So that is what is done by Control X. But if you use AES or DES or any other thing, we need this will be having a very lengthy code. So later we will see how to do that kind of operation also. Afterwards, this is the key thing. We are defining our oracle. So this oracle, what it does, first it will call the cipher, whatever cipher we are going to use. From there, we will get the all the combinations, correct? All the combinations of ciphertext. Following the complete procedure, we will get all possibilities of ciphertext, and that has to be checked with the given ciphertext. So that is what is done here, and the output bit has to be flipped That is what is done here. Afterwards, yeah, this is the uncomputing which we discussed earlier. Because we disturbed the ancilla bits, we have to bring them back, and we disturbed the plain text, so we have to bring them back. So that is what we are doing here. First, we are resetting the ancilla qubits, and actually, because I mean, we need to do the inverse of the cipher process. But since XR is same as its inverse, we are just calling it. Otherwise, we have to do the process in an reverse direction. Okay. Yeah, that's all we have done. And the Grover diffuser operator, as I told you, it's common for all the problems. So I didn't do anything. I just copied from QuizKit website. I just put it. Maybe I'm not going through in detail. You can go through. The only thing we need to give is the right number of qubits which we are interested in. So that is very simple to use. And this is the main code. I have 5 quantum registers, 4 with the size of the problem and 1 with only 1 qubit. This may not be the most efficient method. I'm sure you can come out with a better method in order to reduce the number of qubits. Okay. And there is only one classical register which will help us to take out the key. So we are calling the quantum circuit. We are loading first the plain text. We said 4 digits, right? Then we are loading the key, preparing the key in superposition. Then cipher text is getting loaded. And then we are preparing the output qubit by setting it in minus state. Okay, so what is expected? The key will be 1100, correct? So that is what we will get. Let us see. Yeah, and we once we have set everything, we need to call the oracle. The oracle will mark the required key, and then diffuser, what we are adding here, will amplify it. If it is just 2 bits, 1 iteration is sufficient. Since we have 4 bits, we'll do 2 iterations. Even in fact, 1 iteration also will give a clear demarcation. But in order to have a comfortable difference, we are having the second iteration. And if the problem is very large, we need to do multiple iterations. Afterwards, once we measure the classical register, we will get the key. So let's run it. It takes little bit of time. Yeah, we got it, right? 1100 is a probability of 0.9. So this is a very good probability because we have 2 to the power of 4 combinations possible, which means 16 numbers, out of which this alone is having a probability of 0.9, and the remaining all 15 put together we have only 0.1. So when we plot in a histogram, you will see a very marked difference. So we are able to extract the key for a given plain text cipher text combination, and later when some other cipher text is available, we will be able to get the plain text. Okay, so it is possible to apply Grover's algorithm for symmetric encipherment. So that's what we want to learn. So now we'll move on to simplified AES, because XR is very easy to implement. Let us take one example with things which are very hard to implement. Okay, so AES is the best example, but unfortunately today with available quantum simulators or quantum computer, we will not be able to implement. But still people are working on a lot of optimization techniques, so that when the real hardware is available, we'll be able to crack it with less number of qubits and less number of gates. So for simplicity, we have taken something called simplified AES. Again, it is declared by, I don't know, some researchers. And this paper particularly, it gives the step by step what we need to do with a nice example, so that when at each state, what is the input and what is the output. So this was very useful when we wrote the code. And these two papers really they were implemented, so that was actually the real motivation. You can go through these papers to get a very nice exposure on all the steps involved. But anyway, now we'll see how to write how to generate quantum circuit for the entire process. So simplified AES, there are two simplifications done on AES to get this process. The first and the foremost is the number of bits. So this can handle only 16 bits, okay? And the second simplification is done on a number of rounds. We are doing only 2 rounds here. In the actual case, it is more than 10, right? And similarly, in the actual case, the number of bits is 128 and above. Okay. So, but we are not compromising on other processes involved, like adding a round key, key expansion, substitute nibbles or Sbox, shift rows, mix column, Sbox, shift rows. Like in the AES, the final, the last one will not have mix column. So here also we don't have mix column. And the entire process will generate ciphertext like what we get in AES. The key expansion process is also similar. We break the given key into 2 words, W0 and W1. Then we also have round constant like what we have in AES, 2 round constant because of 2 rounds. Then this operation is similar to AES swap and substitution or Sbox. Then you get W2. Here we may have to do some undoing because your W1 would have got disturbed, so we'll have to get back W1, and you XOR with W2 and W1 to get W3. Similarly, you will do the operation to get W4 and W5, which will be used here. Yeah, I think there is a typo here. Should be W4 and W5. Alright, so this is cryptography method. Now let us see how we need to apply quantum for this. Okay. Yeah, the Sbox. I think you are aware the Sbox is nothing but a lookup table, meaning you have a set of input. For that input you will get some output. So in this case what you can see here is for 0 you get 9, for 2 you get A in hexadecimal. As we discussed earlier, SAS works with 16 bits. And interestingly, there's another paper which I given it in the reference. Those guys actually who published the paper have come out with a software which can generate quantum circuit like this for any type of Sbox required for symmetric cipher. Okay, you can make use of that, but unfortunately it didn't work for this particular one. I have taken this circuit from one of the papers what we saw in the previous slide. So this particular quantum circuit can take any of these inputs and give the corresponding outputs given here. Okay, so the Sbox is difficult, the most difficult one, and the remaining other processes like mix column, adding a key, I mean they are all very simple to do. Anyway, we will see it again with an example. So this time we'll run this file. As we have seen earlier, we need to import all the relevant library functions. The typical any encipherment process will have text and key and generate the plain text and the key and generate the cipher text, correct? Later we need to convert this into an oracle which will help us to get the key. Okay, so but in order to set up that process, we will be doing with a known key. Okay, that's what we are doing here. I'm using only two registers, okay, quantum register and one classical register to get the cipher text. As we have seen previously, we have to load the input. So in this case, it is plain text and the key. Then we have, this is the code for mixed column. Again, very nicely explained in the references. They're all using the reduced polynomial approach. I'm not going to the mathematics piece of it, but certainly, yeah, you can do a lot of research on how to simplify the process or how to make the circuit very efficiently. So we have the subnibble or the Sbox, okay. Then we need to do the XOR operation, right, between the two words of the key. So that is what is done in this function. Then we need to do the Sbox inverse or reverse of Sbox in order to uh, affected key back, okay, because we have seen earlier the S1, sorry, the W1 uh, will get affected when we do this Sbox and swapping operation. So that's why we need the inverse of Sbox, okay. We also need this inverse of Sbox when we put it in the Grover algorithm, when we bring all other aspects of it. Then this function will add the key and the text, okay. Yeah, so these are all the functions. So this is the main program. In the main program, what we are doing is we are loading the key, we are loading the plain text. Afterwards, the round key 1. So we need to add the round key 1. So that exactly is being done here. Afterwards, we need to start the round 1. So round 1, first, what is first? Sbox, shift rows, mix columns. So that's done. Now we need to generate W2 and W3. So in order to do W2 and W3, first we need to add the round key. So adding round key is very simple. So wherever there is 1, you just add a X gate to that particular qubit. So round key is added here. The next step is adding, bringing S box, okay. Yeah, first, sorry, swap and then add an X box. So that is what is done. So with this you will get W2, and before that, yeah, W0 and W1 you have to do. So when you add all together, you will get W2. But in this process we lost W1. We are getting back by doing the reverse S box and reverse swapping. So now we will get W1. The W2 was obtained earlier. So when we do the XOR, we get W3. So that means the round 2 key is now ready. So round 2 key should be added to the text. So that is what is done here. Afterwards, round 2 started. So again, same process we are repeating. We will not go into the details. Okay. And at the end, after doing the final addition of round key, when you measure it, the classical register, you will get the cipher text. So let us see whether we are getting it or not. I'll run all the functions. Okay, so the main code is run. The simulation is done. Let's see how much time it takes. Yeah, you can see here, this is the cipher text. Whether it's correct or not, you can check. But I'm confident that it has done its job. Okay. There are two important things I want to tell you. One, you can see here the cipher text has occurred all that 10 times, because the number of shots equal to 10. So it means even one shot is sufficient, because since we are not using any Hadamard gate or any rotational gate, so it's sufficient to have one time. But when you put it in a Grover's algorithm, obviously you need to run more time, because we will be using Hadamard gates, correct? The another aspect, I don't say it's another issue what I faced here. I started initially with the QASM simulator. So up to maybe the round one, it was working all right. Afterwards, I got into some problem. You know that in the cloud platform, we are given 8 GB, and though sometimes it went up to 7 GB and stopped, or even without raising the memory it was stopping. Then after seeing the documentation, I changed the simulator method to extended stabilizer. It improved a little bit. I could go up to the second level. Again I got some issues. I raised the issue in IBM QuizKit Slack channel. A gentleman told me to use matrix product state method. So which really it has worked here. As you can see, it's working. But still, I have an issue. When I try to modify this to a grower cipher, I'm having problem. Okay, I'm unable to fix it. I try to run it in another local machine which is having a higher memory and better processor. Still I'm having an issue. I already raised the issue in the Slack channel. Possibly if somebody is able to fix it, please let me know. You add it in the comments column. This is going to be vital. But one thing we can be sure that there is nothing wrong in the method, the approach what we are following. But there is something going at the software, the backend software. I hope that will be fixed soon. If not, we need to see whether what else can be done. And yeah. So with that time, my lecture is coming to an end. Told you that some of the references really have motivated, and certainly at the top of the list is always QuizKit websites. They have given nice examples in this site, and this is where they explained the assignment initially, and this is the place where I taken my diffuser operator code. And yeah, this guy, these people have given the best simplified AS explanation with a nice example, giving input and output at each stage, which will be very, very useful for you when you write your own code. And these guys have given very good research, and later these guys have improved the circuit with less number of qubits. And finally, this also will be useful when you use some other encipherment like gift or anything, because they will give you the circuit, quantum circuit for Sbox. Okay. So with this, I'll come to an end, and you can learn more about this. I'll also learn more about other algorithms which can be used for symmetric encipherment. Let us share the information. If you are able to fix the problem what I am facing, please let me know. Okay, so I'll come out with more videos on this subject. So till then, bye bye. Thank you for watching.